This meeting is being recorded.
Okay, so our speaker today is Akshara Prasad, and his title you can see there is Type Semigroups and a Dichotomy for Groupoid at Sister Algebras. Please, Akshara, go ahead.
Thank you for the introduction, and thank you for inviting me to speak, Willie and Gisela. Yeah, I'll be talking about the recent paper I uploaded to arXiv, which is joint work with my supervisor, Ralf Meyer, and Bartosz, who is here. Yes, so yeah, so the talk is about type semigroups and how we get a dichotomy for twisted group or sister algebras using these type semigroups. This is my plan for today, and I hope I can make it in time. So I'll first discuss what the dichotomy is, and why type semigroups is a good setting to go about this dichotomy. And then I'll discuss how to define these type semigroups. And then I'll relate properties of the type semigroup to ideals of the group or sister algebra, and similarly states. And then I'll go about the main statements. And then as an example, in our paper, we applied it to Exel-Pardo algebras. And if time allows, I'll just show the result we have for Exel-Pardo algebras. Okay. So the Banach-Tarski paradox, as most of us know, it led von Neumann to introduce amenable groups to explain the paradoxical decomposition of the unit ball in Rn for n greater than 2. And this led to a split in the world of groups between groups that allow paradoxical decompositions and those that do not. And the border between these cases was whether there exists a finitely additive measure. And von Neumann introduced amenable groups, right? And if you take L infinity of gamma for a non-amenable group, then all its projections will be properly infinite. So purely infinite. So in the world of von Neumann algebras, you get a dichotomy between factors in which all the projections are properly infinite, and factors which admit a trace. So the natural question, whether this dichotomy holds for the case of sister algebras was asked by Cuntz in 1981. The question was whether every simple sister algebra is it either finite or infinite. This was answered in the negative by Rodam in 2002, who showed the existence of a sister algebra which has both finite and infinite projections. The problem with sister algebras is that they may not have any projections, unlike von Neumann algebras. And this problem can happen even more severely in that there are stably projectionless sister algebras. And Blackadar and Kuntz and later Kirchberg showed that every stably projectionless sister algebra admits a trace. So this dichotomy question can be asked for sister algebra as whether every sister algebra is stably finite or purely infinite. We know this for classifiable sister algebras. And the question is whether we can, like given a sister algebra, whether we can detect whether it admits this dichotomy. And that is the motivation for this paper. And Tarski, when he went about explaining this dichotomy, at least the paradoxicality, he noticed that the framework of pre-ordered abelian monoids is a very good framework to explain these things. And that is what we do with the type semigroups as well. So why type semigroups? So on one end, we have sister algebras, and on the other end, we have pre-ordered abelian monoids. And we know that there are these Kuntz semigroups, which are very important to the classification program of sister algebras. And these are pre-ordered abelian monoids as well. And The dichotomy question between stably finite and purely infinite is also very important to the classification program, which has seen tremendous results in the last couple of decades. And also, especially since Tom showed that there exists a sister algebra for which the Elliott invariant is isomorphic, but the Kuntz semigroup is not for the two sister algebras. So they cannot be the same. So since then, we know with the Thomson-Winter conjecture, there was another adjective added to the Elliott invariant in that the Kuntz semigroup needs to be almost unperforated. So the Kuntz semigroups, we know it encodes a lot of information about the sister algebra, but that comes with a complication, right? That it's very difficult to compute. So how can we go about getting an easier version of the Kuntz semigroup, which is easier to compute and also encodes information about this dichotomy? So we have groupoids, and between groupoids and sister algebras, we can form groupoid sister algebras. And from the work of Xin Li and many others, we know that every classifiable sister algebra has a Cartan and hence a groupoid model. So groupoids, in many cases, or in most cases, it suffices to look at groupoid sister algebras and not just all arbitrary sister algebras. So we have this picture here. And the question is, how can we complete this picture? So can we go from pre-ordered monoids to groupoids to sister algebras and encode information about the dichotomy? That is exactly what we do with the type semigroup. So from sister algebras to groupoids, we lose some information, of course. And from groupoids to pre-ordered monoids, we will lose some more information. But if you can encode information about this dichotomy and also some more information that can be useful that we can track about the sister algebras, that is good enough. And that is what we do here. So now I'll go about explaining how we define the type semigroup given a groupoid from which we construct its reduced sister algebra. Okay, so to do this, we'll first need an inverse semigroup basis that depends on the bisections of the groupoid. And this is an auxiliary choice on which we'll have some conditions later on. This is actually useful because it will give us some flexibility in how we want our type semigroup to be. So the set of bisections of a groupoid, it forms an inverse semigroup. You can multiply them and you can take inverses because groupoids have inverses. So I take a subset of the set of bisections and I call it B. And I have three conditions on B. One, B needs to be an inverse sub-semigroup in itself, just like the bisections. And it also needs to be a basis for the topology of G. So there's not just an algebraic condition, but also a topological condition. And when we restrict B to the idempotents, that is the bisections in the unit space that are in B, this needs to be closed under finite unions. So this is our inverse semigroup basis B. What is more important here is O more than B. And using O, we form bounded lower semi-continuous functions on X. So I say f of O. Can you see my cursor, by the way? I hope you can. Okay.
Yes,
so,
we do.
So f of O is his functions is like finite sums of characteristic functions that are supported on sets in O. So these are functions from X to the natural numbers. Now the type semigroup will be a quotient of this f of O based on some relation. To get to this relation, we first need something called the